Hello everyone, my name is Andrija Mihalj, and this is a presentation on my scientific paper. It's called Code Generator for ADAS Software Testing. There's of course an introduction. There's a part about the test environment generator, which is the aforementioned code generator for ADAS systems in the title. And then my work on the paper assignment, which is trying to improve an existing program called the test environment generator, and then of course looking at the results and discussing them, and my conclusion of the improvements made and suggestions for future work, and of course answering any questions I might have gotten. So let's start. Sort of a basic background for ADAS software. The ADAS is a shortened term for Advanced Driver Assistance Systems, electronic systems that assist the driver in driving the vehicle. Sort of a broad term, but basically ADAS systems can directly affect the number of components of cars with the aim of developing a variety of useful features from the viewpoint of accomplishing safer and more comfortable driving, from automatic ignition lights and traffic sign recognition to integration with smartphones. A key factor in the operation of ADAS systems is communication, especially communication among its components, so-called inter-system communication. This kind of process of standardizing communication is something that has to be rigorously tested and carefully written. Those standards are part of AUTOSAR communication models. AUTOSAR is shortened for Automotive Open System Architecture, which is an architecture made for developing test codes within systems, within vehicle systems, specifically oriented on communication. AUTOSAR is in general more of an international partnership of automotive companies whose purpose is to introduce standardization in the creation of software and hardware architecture in the automotive development environment. By simulating vehicle components using software models inside of test environments. The test environment allows for system validation without risking faults on live components, and allows for testing that would be impossible to do manually. Meaning this allows developers and testers to keep the more expensive hardware safe by using safe test environments with strict parameters. And it also allows due tasks which would be impossible to do manually in terms of time or even scale. This test environment is made up of multiple components which form a build basis, which is tested live on hardware. Now moving on to the topic of this assignment, the test environment generator. This is a specific existing solution. To understand it, we need to understand that this code generator receives RXML data, variables, and data types, which it then connects into signals. These signals are then also connected further into ports, and thus the communication between two ECUs is described, from the base data types to where they're going and what their time schedule is and so on. Now the test environment generator itself is in the RTE layer, and it serves to exchange information or communication between the base and application layers. The solution we are looking at in this paper is a Python program which creates and manipulates C files, meaning that it takes input data from ARXML files and creates software components which are then used to build and flash. So we have the input test communication data, or RXML, which goes in, which is then parsed, collected, and put into a sort of hierarchical structure in Python code represented by Python objects. Data that's parsed, of course, get stored away for reference use and debugging and so on. And then the code is generated, which is the little cogs on the breakdown. It uses the templates which come in from the left over here, and it's generated into SVC source code. Now breaking down the individual parts of this test environment generator by order, there's three main parts. There's a parser, there's a storage method, and there's a generator. So this parser assembles the base components of the solution's code into a Python structure of objects, with the primary object being called tom root. And you can visualize this as a tree of Python objects, which mirrors sort of the hierarchical nature of an XML or RXML files. So describing basic data types and then how they're linked and which groups they belong to, which ports and so on. As the RXML unfolds, so does the tom root object structure get filled. To achieve this parsing, the existing solution used LXML Python module, which is a derivative of element tree. The iterative parsing of these input files is done through logic trees and filtering. The main issue I found while examining the existing solution with this parser bit was that the work of the parser becomes redundant on multiple iterations of tag. So when you're testing something, you're of course running the same programs over and over. The multiple iterations of tag can be and were actually being done on the same files. So in order to improve parser, I figured I would have to remove this redundant parsing. As for data storage, it stores the assembled tom root. The existing solution uses the pickle Python module. It's basically serialization storage or using binary data flow. Pickle has a lot of problems. Experts have complained that it could be very unstable, that it's unsecure because you cannot see inside it without opening it or unpickling it, as a method inside of the module is called. The data as it sits as a .pickle file is unreadable. You have to put it into Python code, which is a stark contrast to traditional databases where you can open it up and see tables or linked lists or something. For the generator, it takes the tom root and the templates and it generates the so-called test environment. It basically uses regex to parse and modify these C templates, and then it manipulates data into them. The problem with it was that it sequentially inserted code fragments into SVC template. And basically this meant that the generator, the third part of tag, was the most time-consuming component due to the just sheer number of templates used. So the assignment of this paper became improving this solution by A, accelerating the existing tag so it takes less time to parse and generate output files, and B, making the storage utilize a more stable and transparent method. So moving on to my improvements, what was devised to be done was to implement these solutions in the existing solution, so using Python 2.7, using the program that was used live from RTRK, and shortening the parser became the first part of the work. So shortening its runtime was done by bypassing it entirely if the work became redundant, and utilizing multiprocessing, meaning separating, decomposing work wherever possible, and changing the serialization method of data storage to a relational, human readable database implementation. It should also be noted that the work done in the paper, these improvements on the solution, the code owners were also improving it. So my work closely shadowed what they were doing, but in smaller increments and with less data being visible to me because it is a private project. So the breakdown of my improved solution is as thus. The RXML data is input, but the file structure is verified using a hash string, meaning that whatever the file structure is, whatever the input files are, the input templates, their names, everything is sort of made into an image represented by a hash string, and then the parser moves on. So data gets parsed, it all gets stored, but with the hash string. And then everything goes into storage. This time the storage is not in pickle mode, but in an SQL database. And then when it comes to the generator part, as you can see, I've sort of illustrated here, the generator uses multiprocessing to make a single processing task for every SVC which needs to get generated, which improved the runtime immensely. So concerning the parser improvements, still the LXML Python module was used. I have, after much research, found that it was the most appropriate module to use. So the parser improvements, I still kept the LXML Python module. I saw from my research, I saw no meaningful way to improve XML parsing. What's different is that the HASHLIB Python module is used and a hash is created, which represents the structure of files upon which tag is run. Now, this illustration here shows that when the tag is run, there is a new hash created. This is paired to the hash stored in the database file from the last time the tag was run. And if they are identical, if they match, then the work of the tag is skipped directly into generator, meaning all the data is collected from the storage, it's not parsed again, it's sort of verified to be the same. As for data storage, this became the biggest focus of my work here in the paper. The SQL relational database was used with a module in Python that I found to be the best, which is SQLite. It's an open source module that's very easy to use, with the main improvements being it could now be read, as you can see in this example open program here. You can actually see the data types, you can see what's happening, you can see how things are linked, and this could be done while the tag is not running, which is also a bonus, and it's portable. As for the generator, the main thing that was done was using the Python multiprocessing module, which creates a separate process for each SVC generation. So as for the assignments that were made in this paper, the first one, A, being acceleration. Upon looking at the existing solution, there was of course the idea to restructure the program so that it works differently and then perhaps even faster. But this idea turned out to not be possible, partly due to the time frame of the paper, but also due to the structure and the architecture of how the tag worked, following so closely the architecture of the ARXML files, which were made to an AUTOSAR standard, which we could not change. Acceleration was achieved by validating the structure of files currently being parsed as being identical to those in previous runs, by checking the database of the last run using the HASHLIB Python module. And it was also achieved by decomposing the generation of software components into multiple processes. As for the storage improvement, data serialization using the pickle module was replaced with a relational database using the SQLite Python module, which made it more transparent and readable. And this was done basically by recursively traversing the TOM root and storing its contents into a complex relational database. And this storage method is performed concurrently, parallel with the generator operations to further cut down on runtime. So looking at results, the improvement validation used was verifying that the transferred data from the parsed data to the SQLite database was correct. Also measuring and comparing the tag runtime with the existing solution. The test description for storage was done basically by manually checking side by side what was being put into the SQL database and what was being put into the pickle database, and verifying it this way. Verifying it another way would have been extremely time consuming and difficult due to pickle being unreadable on its own. I would have to have made several methods to print out the entire contents and several methods to then check those with the SQL database. but that is something that is mentioned in my future work section. As for the test descriptions for checking the acceleration of the parser and generator, the existing solution already used a default Python module which could print out when each little section of the program is done. What you see on the screen is a small sample of this. The overall improvements that were made be seen roughly in this chart, where the first line, the E1, represents what has been achieved within fully optimized runtime and using the multiprocessing Python module, but still using the pickle database, so not improving the storage. The second line you can see is using a SQL database, but having it all be as stable as possible, as safe as possible, so no optimization, but still using multiprocessing, which I found to be core and did not even do testing without it, which turned out to be around 11 minutes. The original runtime can be seen as a third column, which is reportedly around 6 hours. The HASHLIB module also introduced acceleration, and it cut down time from 10 to 20% depending on the size of the input files, of course. My main focus was looking at how the SQL database could be optimized. So this is an example of tests done with standard settings. Now, by standard settings, I have focused on synchronous mode and the journal that is made, which logs all the work stored into an SQL database, and this time is around 11 to 12 minutes. But if synchronous is turned off, meaning that the writing can be given to the OS to control, which kind of decreases safety, then the time is almost comparable to the runtime with the pickle module, which is around 2 minutes. And if the journal is only kept in temporary memory, meaning it is not saved as something that you can look at later next to the database, then the time is a bit higher, or at around 3 minutes. In conclusion, the assignment was to accelerate the parser. What was achieved was the parser was accelerated using anti-redundancy measures. The assignment was to make a transparent and more stable, more readable storage, and this was made highly transparent and more secure. And the speed was comparable to the existing solution using, of course, multiprocessing and some optimization. And the accelerating of the generator was done and was greatly reduced thanks to multiprocessing and decomposing tasks into single processes for every SEC. These are the general runtime comparisons, where you can see the first column is using multiprocessing and the pickle storage module, which was already an existing solution. The second one is using multiprocessing and safe, so non-optimized SQL storage. The third option is using the optimized SQL storage, and so is the fourth. The difference is using the HASHLIB module, which you can see that the fourth example takes 10 to 20% longer. But if there is a module, if it's used, then the parser part is skipped and it lasts shorter here, around 2.5 minutes. As for future work which could be done, redesigning the ARXML input files to be per SVC to further decompose the workload, porting the complete program to C programming language. Also, one of the future work was addressing the shortcomings of this storage solution in terms of not manually, so automated somehow, and then you get a sort of check, everything's been parsed correctly, and you can trust it to skip parsing the next time. As for the questions posed by our viewers, the question is here: is there a possible future work to port TEG to C programming language? Since it seems that TEG does not perform CPU intensive processing, maybe speed up would not be significant. Did authors make some feasibility analysis for this direction of their future work? So the work is possible in theory. It has been suggested by senior colleagues with deeper knowledge of the inner and bigger picture project mechanics. Since TEG works with C files to make C files, my idea was maybe create those files instead of manipulate strings to assemble them. So something that's C code that makes other C code. In general, of course, C works a lot faster than Python. that is all for my presentation. Thank you all for your attention, and that's it.